Hello and welcome to this lesson. I hope you are ready because this is going to be the most important lesson of the chapter time complexity. Why? Because in this lesson, I'm going to tell you exactly how I compute the time complexity of each and every algorithm that I encounter. It's super simple. It's my bulletproof structured method that you will see that naturally with practice, you're going to find super easy. You're going to master it and you are going to be able to basically compute each time complexity, maybe except those harder ones in which you need to do an amortized analysis, but that's a different thing. We are going to also get into that. So let's keep it simple, right? Now, in the previous lesson, I have told you that basically when computing the time complexity of an algorithm, we need to compute, right? We need to count how many constant operations our algorithm does, and then express those numbers, right, in terms of some number that is in the input, right, or the input size. For example, when we had an array of length n, then the number of constant operations has to be expressed in terms of n, right? Maybe big O of n, maybe, I don't know, 3 crossed n, which is also big O of n, right? Big O of n log n and all that stuff. So here, I'm going to make it actually even simpler for you. So each algorithm consists of lines of code, and each line of code is actually of one of these two types, right? So the first type is what I like to call atomic operations. The atomic operations are not only constant operations, right? They can have a time complexity which is greater than big O of 1, but there are basically those lines which are not for or while or some repetitive loops, right? So most of one algorithm's lines of code are actually atomic operations, and they can be mathematical operations, plus, minus, multiply, division, right? They can be a return. Maybe inside a function, we return an integer, we return a string, or we return maybe nothing, right? If that function is a void one. It could be a break if we want to break out of some repetitive loop, maybe some for or a while. It could be a condition, right? Maybe an if or an else. We check if something equals something, right? That's a condition. It could be a syntax sugar, right? For those languages, maybe JavaScript, maybe Python, in which, I don't know, for example, in Python, you can concatenate two lists together, right? You can say that list 1 plus equals list 2, right? I don't know if this is exactly the syntax sugar, but you get what I'm saying. It's basically a way of writing very nice without a for loop or stuff like that you are going to add all the elements from here to here, right? And maybe a function call, right? So it could be a function that we have defined. Maybe we have defined a function and we want to call it, right? We have in one line, calling the function, do stuff, and that's it, right? Or maybe we have the function sort, which is from some library, right? Which is, from that programming language, basically. So these are the atomic operations that I'm talking about. Again, it's super simple. There are basically those lines or those pieces of code which are not for loops or while loops, right? And as you can see here, these atomic operations are actually constant, right? So only making an if-else statement, right? If we, computed what needs to be computed, right? Because of course we can have an if and we can call a function here, right? If do stuff, for example, of something, I don't know, equals something, right? Now this function call, of course, maybe this is big O of n. Now we can't say that the whole if statement is big O of 1, right? But when I say condition, I'm just talking about this equal, or maybe not equal, or maybe less, or maybe greater, stuff like that, right? So, condition after everything is computed is constant. The break is constant. The return is constant. Again, after having computed what we need to compute, we can do return, do stuff, and call again the function, and that's big O of n, right? So only the return, only this keyword. These operations are constants, right? And we have the syntax sugar and the function calls, which of course are not necessarily constant, right? They could be constant, they could be big O of n squared, depends, right? Perfect. So First of all, when I see an algorithm, I am looking at these atomic operations and I think about what is the time complexity of each and every one of them, right? Of course, when I see one of these, I know it's constant. When I see a syntax trigger or a function call, I have to look at my function call, right? If I was the one that wrote it and it's not from that programming language, or I need to think about the function from the language or the syntax trigger and really know what is the time complexity of that, right? Cool. Now, of course, the atomic operations are not enough to build an algorithm, right? You will rarely see an algorithm that only consists of atomic operations, each of them happening once and doesn't have any for or while loop, right? In most of the algorithms, we need to do repetitive things. We need to do an atomic operation or maybe a sequence of atomic operations for more than once, right? And this is where the for and the while loops and every repetitive loop comes into play. So inside the loop, we can either have atomic operations, right? For example, if we want to print the first 100 numbers, right? What do I have? I have a loop, which is a for loop, and I say I from 1 to 100, right? And what do I have inside? I have print I, right? So print I is a function call, depends on the language. In our scenario, is going to be constant. So basically this print I is our atomic operation, which is going to take place for 100 times, right? So we can have one atomic operation, one sequence of atomic operations. Maybe I want, after printing it, to, I don't know, increase a sum, right? So I increase a sum by this number, and then I want to do other stuff. Maybe I want to call a function. Maybe I want to return. Maybe I want to break, whatever. But also inside the loop, we can have another loop, right? Maybe I want to print the first 100 numbers, but I want to print each and every one of them for 100 times, right? So what will I do? Of course, I'm still going to need my loop, right? Which is going through each and every number from 1 to 100. But now I not only have this print I need to do this for 100 times, right? So I need a loop which is going to execute my atomic operation for another 100 times. So this is exactly why here I'm going to need the second loop, which is going to help me print the number I for 100 times, right? So this is it, guys. What I want you to remember for now is that we have atomic operations, which are basically not loops, and we have loops. And inside those loops, you can either have another loop, and inside that maybe another loop and another loop, or you can have an atomic operation, right? So what I want you to realize is that the structure of each algorithm is something recursive and actually looks like a tree, or to be more specific, a forest of trees. Now, I know we haven't studied any of those, but don't worry, don't be afraid. It's actually way simpler than you think. Let's take this example and I show you exactly what I mean by that tree, right? So if I take a look at this algorithm, for example, right? Here I have a for loop, right? And inside this for loop, I have my two atomic operations, right? So the root, quote unquote, of this algorithm is the for loop, right? All the action, all the atomic operations happen inside this for loop. So I'm going to have a node, right? Which again is the root, which represents the for loop. Now inside the for loop, everything, as I've told you, happens. So what I'll do is that I'll make actually a node here, and this node is going to represent this piece of code, right? So each time in the for loop, do the piece of code, do the piece of code, do the piece of code, right? And this piece of code actually consists of two atomic operations. The first one is print. So I'm going to have a sum for the print operation. So here I have the print, right? And of course, the second one is the addition. So I'm going to have a sum for another sum for this addition, right? So if you take a look at this tree, what happens in terms of how the algorithm runs is that we take a look at the first node, which is the root, and we see that this is a repetitive loop. What this means is that on each iteration of this loop, each time we basically enter it, we will have to execute the sum, right? So here is our loop, right? We enter the for loop, execute the sum, go back, execute again the sum, go back, execute the sum until we are finished and we exit the for loop. Now, this sum, because it doesn't represent a repetitive loop, when it is executed, what we are going to do is actually execute its sums in the right order, right? So when this should be executed, this piece of code, I'm going to take a look at the first sum. I'm going to execute the print. Then I'm going to take a look at the next sum. I'm going to execute the addition, and then basically I'm ready. So what happens? This piece of code finishes, and of course we return to the for loop, okay? So this is how the structure looks like. Now let's take a look at the second algorithm. What do we have here? We have two for loops, and we have a print, right? Which is the only atomic operation. And let's take a look at the first for loop. As you can see, this one is also the root of the algorithm because everything else happens inside it, right? This for loop and the atomic operation, they are both inside this for loop, right? So this is going to be again the root of our algorithm. Now, we take a look at the next for loop. What happens here? Well, these two are nested for loops, right? This is definitely the son of this one because every time we enter the first for loop, we are going to execute the second one. So I have my son, which is again another for loop, right? And then inside this for loop, what happens is that, of course, I have my atomic operation, which is this print, right? So this is how the second algorithm looks like in terms of structure, right? Again, what happens each time I enter this, I have to execute this. So I have a loop here. Each time I enter this, I also have to execute this. So I have another loop here, and then we move back, right? So I equals 1, enter here. Cool. J equals 1, enter here. J equals 2, J equals 3, go back, and so on and so forth. Now, what I always do when I want to compute the time complexity of some algorithm is that I first figure out what is the structure of that algorithm. And if needed, I also draw it on paper, and then I follow a simple strategy in order to compute the time complexity. And I'm going to show you the strategy right now. Let's take the first example again, right? I take a look at the structure. I always start from the bottom of the tree and work my way up until I hit the root where I'll actually have the final time complexity of the algorithm. So I'm basically starting with the bottom, right? With the leaves. What is a leaf? A leaf is a node that doesn't have any children, right? So as you can see, my print and my plus are the leaves. Now, of course, the leaves are always atomic operations, right? And it is your job to know what is the time complexity of that atomic operation, right? Whether it is one of these or one of these, you have to know those time complexities, right? There is no way of computing it otherwise. So I know that the print is constant. So I know that this is big O of 1. I know that the plus is constant. So I know that this is a big O of 1. Awesome. Now I move up to the father. So knowing the time complexities of each piece of code that is part of the greater piece of code, the father node, how should I compute the time complexity of the father's one? Well, that's pretty simple, right? I'll just have to add them together because I know that the father executes this and then executes this. So if this is constant and this is also constant, of course, I can't write big O of 2 here. What I'm going to do is this piece of code is also constant. Awesome. Now I know the time complexity of this. What's going to be the time complexity of the father? Well, this is interesting because this father is a loop. Being a loop, it means that it executes this piece of code multiple times. So I know the time complexity of this piece of code, but in order to know the time complexity of the whole algorithm, I need to know for how many times this piece of code will actually be executed, right? So yeah, this is big O of 1, very cool, but for how many times do I execute it? Do I execute it once? So it is still constant. Do I execute it 100 times? Do I execute it maybe n times if we had an integer n and stuff like that, right? So when we encounter nodes that represent repetitive loops, we always need to ask ourselves the following thing. How many iterations? This is the question, right? How many iterations does this loop perform? And in order to answer this question, of course, we have to analyze that loop. It could be a simple loop, right? Like this one. I starts from 1 and gets always incremented until it hits 100 and yeah. So it's definitely that we have 100 iterations here. But it could be a more complicated loop, right? It could be a while loop which has a condition, and yeah, you have to actually figure out when that condition is not being satisfied anymore, right? So yeah, this is something that obviously I can't learn you. This comes with practice. You are going to encounter a lot of loops and you are going to be able to figure out how many iterations each of them does. For this example, it is definitely 100, right? So yeah, pretty simple. So I can say that this for loop makes 100 iterations, right? And for each of the 100 iterations makes this constant. So yeah, obviously I can't write big O of 100 because we don't want constants here. So yeah, just for the sake of it, like to make it pretty, let's say instead of this 100, I had an n here, right? So I goes from 1 to n, which is some integer, I don't know, given in a function or stuff like that. So instead of 100, this for loop makes n iterations, obviously. And for each of the iterations, it executes a code that has constant time complexity. So we are going to multiply them together, right? So here it is the multiplication, and here we basically had the addition. Now let's take the second example. Again, what do? I start from the bottom, right? And I know that the print is constant, time complexity. Then my father is a for loop. So I have to answer how many iterations does the for loop do? Well, 100, right? So for 100 times, I'm going to have this big O of 1. And then again, this also does 100, right? So the total number of iterations is 100 squared. And just for the sake of it, right, to make it pretty, I can write here n and here n. So I can say that actually this is big O of n, right? And this does n iterations, right? N iterations for each and every one of them, big O of n cross n is big O of n squared, right? So yeah. All right. So the three rules that we have learned in these two examples are: the first one, we always start from the bottom, compute the time complexity of those nodes, which are initially leaves, and then compute the time complexity of their fathers and so on and so forth until we hit the root where we will have the final time complexity of the algorithm. Rule number 2. When you want to compute the time complexity of some node, which has multiple sons, you are going to add the time complexity of each son, add them together, and have the final time complexity of the parent. And then, when you try to compute the time complexity of some node, which represents a loop, you are going to ask yourself how many iterations does the loop do, and multiply that number with the time complexity of the son, and this is how you get your final time complexity. And also for this rule, you need to be careful about one thing. And that thing is whether the number of iterations that this son node does depends on the parent loop or not. If they are completely independent, then yeah, it's perfectly cool. You can multiply those two and you'll get your time complexity. For example, here, right? They are completely independent, right? This for loop will definitely perform n iterations, right? No matter the value of I. So yeah, this is always big O of n. This for loop does n iterations. They are independent. So definitely let's multiply them together and we have the time complexity. But let's take a look at another algorithm. What would happen for this algorithm? I takes each and every value from 1 to 100, but j takes every value from 1 to 100 minus I. So actually, the number of iterations that this for loop is going to do is actually dependent on the value of I, right? For I equals 1, I go from 1 to 99. So I have 99 iterations in this for loop. For I equals 2, I go from 1 to 98. So I have 98 iterations in this for loop. I equals 3, I'm going to have, of course, 97. And so on and so forth until I equals 100. And I'm going to have 0 iterations, right? So they are not independent anymore, right? I can't say something like this. This does a total of 100 iterations, and this one does a total of 100 minus I. Let's say it's at most 100 and multiply them together. The number you're going to get is not the right one. The right number is this one, 99 plus 98 plus 97 plus ... plus 0. So what you are going to do when one loop depends on another is that you are going to actually take into account each and every value of this I, right, inside the first loop, and for that value add to our sum how many iterations this does. Again, I can write my tree, no problem. I have the first for loop, I have the second for loop, and I have the sum, which is the print, right, the atomic operation. Now, of course, I know that my print is a constant, a big O of 1. I know that this for loop, how many operations does it do? This for loop, how many iterations does it do? Well, it's not 100 anymore, right? From 1 to 100 minus I, it's actually dependent on I. So it's going to be 100 minus I. 100 minus I. And how many iterations does this for loop do? Well, this one technically does 100, right? So again, it's not like I can multiply these two together and I have my time complexity. No. What I should do is compute the sum of 100 minus I, right? The number of iterations my son does for each of my values, right? For each I from 1 to 100, right? In some algorithms, we are going to be able to compute these types of sum. For example, here, right? I know what is the sum. 99 plus 98 and so on and so forth plus 0. I know this is a Gauss sum, right? And I know the formula for it. It's 99 crossed 100 divided by 2, right? So yeah, this could be done. We are going to have some algorithms in which computing a sum like this, which is way more complex, is not going to be possible. And in that scenario, we are going to take an upper bound for the number of iterations that are performed here. But again, that is a little bit more advanced. I'm not going to get into the topic. What you need to remember here is that when you have nested loops, always ask yourself if they are independent or not. And if they are, multiply their numbers of iterations, and that's cool. If they are not, try out each and every iteration of the first one and add to a sum how many iterations the second one is going to do on that specific iteration, right? So yeah, that's it. That's it, guys. To sum up this lesson, remember that each algorithm consists of atomic operations and loops. For the atomic operations, it is your responsibility to know the time complexity of each and every one of them, right? If it is so simple like this, it is going to be constant, but it might be a function call. That function might be written by yourself. So you're first going to need to compute the time complexity of that function, right? Or it could be a function from the language, which you should know what are the time complexities of those functions, or could be a syntax sugar. Again, you should know the time complexity. Now, after figuring out what are the atomic operations, you are going to figure out what is the structure of your algorithm, right? And by that, you are going to imagine or even draw this tree, and you are going to classify the nodes as nodes which are quote unquote empty, right? They represent pieces of code. Nodes which are representing atomic operations like this print or this plus, and nodes which represent the loops, right? There should be only 3 types of nodes. Then you are going to start from the bottom of the tree and compute the time complexity of the leaves and their parents and their parents and so on and so forth until you hit the root, which is your final time complexity, right? When you have the leaves, they are all of them of the first type, atomic operations, so you know their time complexities. Now, when you deal with the second type of nodes, which are nodes that are empty or represent pieces of code, what you're going to do is, of course, you are going to take a look at the sums. You know their time complexities, add them together and get the time complexity of that parent. And when you deal with this type of nodes, right, the loops, it is very important to figure out in which scenario you are. Maybe you are in a scenario in which the loop and the sun are independent. So the number of iterations from the sun could be an empty sun, could be another loop sun, doesn't matter, doesn't depend on what happens here. And in that scenario, just multiply the number of iterations of the parent with the time complexity of the sun. And if they are dependent, like in this scenario, you will have to express the number of iterations of the sun depending on what happens here. In this example, what's the value of I, right? And then compute the sum. And the sum, after you compute it, if you can, is going to be your final time complexity. If you can't and the sum is too complicated, then you are going to take an upper bound. Like in this example, if I couldn't compute the sum, it was very complex, let's say minus I squared plus 2 cross I or something like that, I'm going to say that, all right, the number of iterations is at most 100, so I'm going to use this value, right? Yeah, this is what you have to remember, guys. And don't worry, we are going to practice a lot and we are going to really master this. That's it. I'll see you in the next one. Bye.